Okay, let's go for the next topic. The next topic is torque. The symbol for this quantity is tau, and torque is defined as the cross product of R cross F, where force is the net force in this case, and R is the position vector respect to a origin. Imagine, for example, we have this object, right? And we want to rotate this object. This is the x rotation, right? Zero origin, right? And we apply a force in this direction, right? F, correct? Now, we create a rotation, correct? We create a rotation in that direction. Perfect. But what happens if we change the position of the force? For example, right here, let's place it right here. Do we create the same effect? No, right? Even though we create torque, but the effect is different, is less. What about if we apply a force in this direction? Well, if we apply a force, we are dealing with the same force, right? It's happening that we have no rotation. Means then that to create rotation, we need two quantities. We need a force and we need the distance, right, of the point where we apply that force to the x rotation, right? This quantity is called, again, the position vector respect to the origin, r. Correct? Now, when we multiply these two, we create a new quantity, right? And we call that quantity torque. And according to this definition, right, the new quantity is going to be equals to R cross F. What is cross? Well, let's go back another situation, right? A general situation. For example, imagine that again we have the same problem, the same object to be rotated. Correct? And now we apply a force, let's say, in this direction. Correct? Okay, perfect. Let's see what happens in this case. We have the angle theta, right? And we have the position vector. Perfect. Now, we can break this force into components, right? One component perpendicularly to R, and one component, right, parallel to R. This is perpendicular, and this is parallel. Correct? Imagine that we want to rotate this object. If we pull the object right in this direction, let's say in this direction, we cannot rotate it. If we push the object right in this direction toward the x rotation, we cannot rotate the object, right? So to rotate the object must be a force perpendicular, right, to, in this case, to R, correct? In this situation again, the component that produces a rotation of the force is this one, the perpendicular one. This parallel component doesn't produce rotation. So in general, then we have that the torque tau is equals to the product of this position vector times the component, right? The component of the net force, which is perpendicular to R, right? And that component is F sine theta, correct? And we reduce this form in this way, right? R cross V, F is actually RF sine theta, correct? Perfect. Now, because it's a vector, it has direction, because look, if we go in this way, right, we have one direction. If we're going this way, we have another direction, correct? So going counterclockwise is positive by convention, and going clockwise is gonna be negative by convention. Perfect. So it's a vector, and what should be then the symbol for vector? Well, in this case, the unit vector, right, perpendicular to the plane formed by these two vectors. For example, if R and force, right, are in this plane, right, what should be the direction of the torque? Well, we use the right-hand rule, right, and the direction goes in this way, right? We use the direction of motion in this way, so the perpendicular one is gonna be the direction of torque, which is represented by this n, means the normal. It's normal, right, to the plane of these two vectors. Got it? Okay. Now, let's continue on this picture, right? We are in that picture. Imagine that we have this situation right here. We found that the component that is producing the torque is the perpendicular one, right? The component of the force, right? This one, this perpendicular component, right, is causing the torque. the rotation. Got it? This is R, position vector, right, in the net force. Perfect. Also, we can project the line of action of the force, right, in this way, and we can create a right angle to make, right, these two angles the same. Perfect. Now, in this picture, we can call this R perpendicular, correct? But this R perpendicular is just equals to R sine theta, which is the same as this one, R sine theta, correct? So when we plug this value right here, and this one, this perpendicular, right? This perpendicular component is equals to F sine theta. We have another way how we represent the torque, right? And it's this one, the magnitude, right? It's gonna be torque is equals to R perpendicular times the force, or equals to R times the force perpendicular, correct? Where again, this perpendicular component, right, is just R sine theta, or this perpendicular component of the force is F sine theta, correct? Perfect. Now, this helps us a lot solve problems in many cases. For example, imagine that we have this object, a general object, right? Any object right here, in this x rotation, imagine x rotation, right? And we apply a force, right, in this direction, and we apply a force, let's say, in that direction, and a force, let's say, in this direction. What should be the torque? The torque that is created on this object? Well, this force creates no torque. Why? Because it is in the direction of the x rotation, correct? Now, what about for this force? Let's call this F1, F2, right, and F3. For F3, right, this is the line of action, correct? Now, if we can find the perpendicular distance to this line of action, which should be this one, let's call it R perpendicular, then what should be the torque produced by force 2 is equals to R perpendicular times F2. What should be the torque produced by this force? Well, it's gonna be what? R perpendicular times what? F1. But what is R perpendicular? 0. So it's equals to 0. There is no perpendicular component like in this case. What about for this F3? Well, this is the line of action, right? It's gonna be the perpendicular line, right? R3. So torque produced by this force is equals to, right, R perpendicular times F3, right? And another way how we can use torque, right? When we have the component, right, which are perpendicular to, right, the force, right? The are perpendicular, right? Perfect. For example, let's do one example to find the difference between using these two force torques, right? Let's say the magnitude is equals to RF sine theta, and also we have that we can use the magnitude equals to R perpendicular times the force, or the force perpendicular times R. Correct? Okay, let's do another example to see how we can apply these two equations in the same problem. Okay, let's do it. Imagine that we have a crate, right? We have a crate, right? And this is a cubed, correct? And imagine that we want to just barely create a rotation, right? And we apply a force in this direction, correct? This is a pivot right here. This is the origin, the point at which the rotation is happening, correct? Now, let's find the torque. Let's find the torque using these two ways. Okay, let's do it. First, let's find forces acting. Well, we found that this is a force acting on the subject. What else? Well, we have this one. Imagine we have this one is the normal, right? And we have, imagine, friction. But this forces goes toward, right, the origin. When the force goes toward the origin or the extra rotation, there is no rotation, right? So torque is 0. So these two forces produces 0 rotation, right? 0 torque. Okay, perfect. Now, let's see what else do we have. We have this force, yeah, this force produces a torque right in this way. What about the center of mass, right? The gravity, the gravitational force, right, represent the center of mass, which is at that point. Okay, so we have another force, which is mg. Okay, these are the only two forces that can produce torque in this example. Okay, perfect. Now, let's see what should be just the force requires to barely rotate, right, this crate. In this case, the torque is still 0. Okay, let's use this equation. Okay, so for this equation we have, right, that torque is equals to F, right, times the distance, right, and the position vector, correct, times sine theta, correct, plus, because we're dealing with vectors, right, when we're dealing with vectors, we're dealing with torque, right, the net torque is equals to torque done by a vector of force 1 plus, right, the torque done by another force, right, and so on, and so on. Got it? So we can represent the net torque in this way. Okay, right here we're dealing with the net torque. So we have two forces acting, this force and the weight. Okay, now these are vectors, right, and they have directions. What about for this force? What is the torque produced by this force? Well, the torque is gonna be right in this way. In which direction is that way? Negative. Remember, the convention is going counterclockwise is positive and clockwise is negative. So this component is gonna be negative Fr sine theta. What about this force? This force produces a torque right in this direction. Got it? So it's gonna be positive plus mg, right, sine theta. Right, let's call this theta 1 and theta 2 for example. Okay, let's do it. Let's do it. Now let's find the angles and r, correct? Okay, let's do it right here. So this is the distance r. Let's call this, actually I'm missing, right, another r right here, right? It's gonna be what? mg r, let's say r2, and let's say this r1. Okay, perfect. Now, the distance from here to here, right, the position vector from the force to the origin is r1. So what should be that magnitude? Imagine this is a square, this is L, right, and L right here, right? So the magnitude is gonna be, right, L is square root 2, correct? This distance is, right, L is square root 2. Perfect. Now let's continue right here. This is equals to negative what? Negative force, right? L is square root 2, right? Sine, what is the angle in this case? Well, the angle is gonna be 45 degrees, right? Sine 45, right, is 1 over square root 2, correct? Correct, which is, some sine of 45 is what? 1 over square root 2, correct? Perfect. Plus what? Plus mg. Now what is r? The position vector for case 2, well, it's gonna be half this one, right? It's half. So what do we have is equals to L, right, square root 2. Let me do it. L one more time. L square root 2 divided by 2, right, times sine theta 2, right? The angle is the same, right? These are the angle for this one. Okay, one more time. This is the angle theta, right? It's the same angle, right? This is the same angle theta and theta right here, right? The same angle. Okay, perfect. And then what do we have? Is equals to 1 over square root 2. Right, must be equals to 0 again, because we just barely made the torque. Great. Now, what should be then the force, the minimum force required for these conditions? Well, when we solve for force is gonna be equals to mg, right? mg divided by 2. Correct? Perfect. Now, instead of dealing with angles, let's go to this case, right? Using the perpendicular conditions. Okay, let's do it. So for this case, look, second case, we have, this is the the cube. This is L, this is L. Now this is the line of action of the force, right? So can apply a force, place the force on that position. Also, right, we have that this is mg, right? Now this is the perpendicular r, right, for mg. This is acceleration, and this is the perpendicular distance, right, to the force, correct? Now let's do it. So what do we have then? Torque is equals to negative F times cross times the perpendicular distance, which is in this case L, right, plus mg, which is the force, times this distance was perpendicular to the force, which is right, L divided by 2, right? L divided by 2 equals to 0, right? From here, what is the force then? The force is equals to mg divided by 2, correct? And we get the same answer. But which one is easier and faster? This one, right? This case, we don't need to use, right, sine, cosine, and so on. Sine in this case. Got it? Perfect. Now, let's continue. Actually, look, for this example, right, the angle that we have right here, correct, is gonna be cosine theta, right? For this case, right, it's gonna be cosine theta, okay, cosine theta. But because this case is 45 degrees, right? We have the same condition, correct? Okay, great. Now let's continue. Let's continue to the next topic. Imagine that now we're looking for the case when we use Newton's second law. Okay, let's go for Newton's second law. Perfect. Okay, let's do it. Now let's go to the case when we use force equals to ma, and let's apply this equation to torque, right? From here, torque is equals to, this is case when the angle is 90 degrees, right? To simplify the calculations, so sine 90 degrees is sine 90 degrees is 1, correct? Okay, so this equals to what? R, right, times mass times acceleration. Again, we are using Newton's second law. And what is this? This is equals to R mass, but what is the acceleration in function? Remember, we are dealing with rotational motion. Remember, we have that acceleration is equals to R times alpha. When we apply this definition right here, this quantity right here, what do we have? This is R times alpha, correct? And then what do we have right here? We have this equals to m r squared times alpha. We are already familiar to this quantity, right? This quantity is the moment of inertia, correct? So remember, moment of inertia for one particle is equals to m r squared. So this equals to moment of inertia times alpha. So we have another quantity, right, that give us, right, the same torque, right, which is moment of inertia times alpha. Correct? Perfect. This is good for solid and for particles, right? We are dealing with one particle. Also, we can deal with solids, right? With solid. Remember, just change the moment of inertia for solid is equals to either r squared, right? Dm, right? For solids. We know that from the previous chapters. Okay, great. Perfect. Now let's go to another problem, well, another concept. Let's go to work and energy, right? Work and energy. Okay, let's start with work. Imagine that we have this, again, this acceleration. We have an element, right, on mass, the m, right, and we apply a force, the F right here, right, and of course it's gonna be rotating, correct? Ladies, it's in this position, correct? We can represent this in this way too. Look, this is acceleration, this is the element on mass, the m, correct? And now this is the final position, right? It goes in this way. Perfect. So what do we have right here? This is r, right? The radius, curvature. right? And then we have this element, right, of angle. We can represent this also, right, as the S, right, the S. Also remember we have a force, we apply a force at the beginning. Imagine this is a force, right, applied to that mass, right, the M. This is the force, correct? So this is the angle phi, right, between, right, this position vector and that force, and we create, right, that angle or rotation. Okay, perfect. Now let's see what happens when we apply torque. Let's see, what do we have? We have that S, remember, is defined as R times theta, correct? Let's take the this infinitesimal changes. So what do we have? ds is equals to r d theta, correct? Okay, perfect. Now let's make the product of these two quantities, right? R cross this component, right? The component that produces the torque, remember? So what do we have then? We have that this is R times what? Times the force, right? Sine theta, correct? The force, remember this, we're dealing with work, right? Okay, work. Let's go back. Work, this element of work is equals to this force, right? Force times what? Times this element, right, of path, right, of distance. Perfect. Now, what do we have? Actually, this is the cross product, the dot product. This is the dot product, correct? Perfect. And then this is equals to what? Let me go back to this part. Remember, we're dealing with work. Okay, perfect. So we have this product again, but the motion goes in this way. So it's gonna be the force gonna be perpendicular. Right? It's gonna be then gonna be what? F, right, sine phi, correct? And what should be this ds? ds is what? ds is r d theta, so it's equals to r d theta, correct? Perfect. But what is this? What is this quantity? This quantity is just this quantity right here, right? So this element of work is equals to, right, torque, tau, right, tau d theta, correct? Tau d theta. Perfect. Now, what happens if we go to tau, the torque, right, represented this way? Okay, let's do it. So it's equals to what? Moment of inertia times alpha d theta, correct? Perfect. Now this is equals to what? Moment of inertia. But how do we define alpha? Alpha, remember, instantaneous is equals to change in omega, right, respect to time. Okay, let's do it. It's gonna be d omega, right, respect to time, d theta. But also we know that instantaneous angular velocity is equals to d theta by dt. If we move this quantity right here, we have that's omega, right? The instantaneous angular velocity. So from here, this equals to moment of inertia omega d omega. Correct? Perfect. Now, at the end, what do we have? Work is equals to the integral, right, from initial angular velocity to final angular velocity of moment of inertia omega d omega. Correct? Perfect. Now, what do we have? We have that is equals to, okay, work is equals to moment of inertia, right, omega squared divided by 2 from what? From initial angular velocity to final angular velocity, right? And this is equals to, right, moment of inertia omega, right, square divided by 2 at the end, right, minus, right, moment of inertia, correct, omega square, right, divided by 2 at the beginning. Okay, the initial one. Perfect. What is this? Well, remember from the previous chapters we defined that the rotational energy is defined as 1/2 moment of inertia omega squared. When we apply this definition right here, what do we have? This is equals to actually the change in the rotational kinetic energy, right? So we found that similarly to the linear motion, right, in the rotational motion, we have that work is equals to the change in the rotational kinetic energy, where rotational kinetic energy is defined as 1/2 moment of inertia times omega squared. Correct? Okay, perfect. Now, let's go back to this equation right here, right? What do we have? This element of work is equals to torque, right, times d theta. Now, if we divide this by time, right, by time dt, right, work divided by time is just power, right? This is power, right? Instantaneous power. What should be this one? Again, one more time, this is omega, right? Omega. Perfect. So power then is equals to what? To the torque times omega. So we have another quantity that helps us, right, to work with rotation, right, using torque. So we have that power is equals to torque times omega, the angular velocity. Correct? Perfect. As you can see, these quantities, rotational quantities, are very close related, right? Or they have the same form as the linear quantities. Let's match these two. Let's see what happens. Okay. See, we have, for example, in the linear case, right? We have linear, right, motion, right, and rotational, right, motion. Okay, in the linear motion we have force, right? Force, we have work, right? What else do we have? We have kinetic energy, right? We have what else? Power. We have power, and we have power. We have the linear momentum. Correct? Perfect. For force, remember, force equals to ma. Right here, the function, the quantity that has the same function as force is called torque, right? Tau. Torque is equals to force, right? The cross product. We can use the cross product, right? The cross product, right? R cross F, correct? Perfect. For work, we know that work is equals to, what's work right here? The net work, right? The net is equals to the change in the linear kinetic energy or translational kinetic energy. Right here, right? We found that work is equals to, again, the change in the rotational kinetic energy. But what about kinetic energy? Well, we know that it's equals to 1/2 m, right, v squared. Right here in the rotational case, right, kinetic energy is equals to 1/2 m, not mass, we use moment of inertia, right? Moment of inertia times omega squared. Power, we just found power, right? Power is equals to where's power? It's right here, right? It's equals to force times velocity in the case, and right here is gonna be torque times omega. Finally, we have linear momentum is equals to, where's linear momentum? This is where's power? I forgot power. It's not power here. This is power. Perfect. Now linear momentum is gonna be mass, right, times v. We don't know yet the angular momentum. The angular momentum is L, right? It must be equals to, as you can see, these quantities are related. Mass goes to moment of inertia, and v goes to omega. Correct? So mass goes to moment of inertia, and v goes to omega. From here we can deduce, right, that angular momentum is just moment of inertia times omega. Okay, and with this we finish this section on torque. See you in the next one.